Okay, our next speaker is Michael Goldstein from Durham. He's going to talk about inverting the Pareto boundary based linear optimization under soft constraint.
So again, thank you to the organisers for the invitation. So I've spoken at each one of these workshops because I just couldn't say no. Okay, so the last three talks were a kind of my back pages talks. So I thought, it's the last one. Let me do something where, instead of the I was pseudo-polish of something you did in the past, it's kind of what we're doing now. Okay, so, and in fact, I have a question at the end. I hope I get to it, where I'd really value your feedback. Okay, so I've been told by experts, because we had that guy yesterday who said that presentation was really important. Okay, that any problem you can describe, particularly if it's a decision problem, there should be a version in terms of pizzas. And once you understand the pizza version, then the problem is clear. So let me try and do the pizza version of this quickly. Okay. So imagine that I have a group of people and I have to put in an order for the pizzas for them. So an order might be 1 margarita pizza, 1 half blue cheese, half Hawaiian. You can imagine I have a series of, so all I can do is, some people would like that, okay? The pizzas are going to be divided at the end, so nobody actually has to have both, but it just is a way of getting them in. So the process is that the person who's going to put down the order is allowed to do this. He can write down the possible order, it's then sent to the group in another room, they chat about it, and they give back a niceness score. Yeah? So, the person's aim, so it's like an analog computer. Okay, so the optimization problem is to find the order that will give you the best niceness score. Okay, now you soon realize when you do this that you could just get like every pizza in the world twice, and then everybody will be happy. But so there are constraints. So there are either hard constraints or soft constraints. So the hard constraint would be, he says, how much money do you have, guys? They open their pockets and we have £20. That would be a hard constraint. More likely, and when we're talking about decision support, any hard constraint can be turned into a soft constraint. They say, well, we have our cards, but not too much. Okay, so money is a soft constraint. Okay, so what is decision support for this problem? Decision support would be effectively to say, what is the trade-off between niceness and price, and what kind of pizzas orders sort of work at different sort of levels of the thing. Okay, so the Pareto boundary. Okay, so here it is. So here's price, and here's nice. Yeah. So the Pareto boundary will be a curve. Boundary. Yeah. So every point on that curve, there is at least one pizza order that would actually give you that price and that nice. And for any particular price, you can't get a niceness more than the point on the curve. Okay, so there's everywhere down here there are pizza orders that you could actually get. There's nothing up here. Okay, so your aim is to identify the curve and invert it and find the collection of different choices for each one. And then, because we're talking about decision support, so that realistically they really don't know how nice a pizza is going to be. They say, well, I thought putting pineapple on blue cheese would be great. It turned out to be disgusting. So there's doubt that, and maybe the price as well. They've got an old price list, So there's a lot of uncertainty at different levels. Okay, so that's the pizza version. Okay, so inverting the Pareto boundary. So I'm looking at sort of decision support for this problem, and I'm going to do it by Bayes linear optimization. Okay, so let me get on and actually, I'm not actually going to do the pizza problem. Okay, so my involvement effectively in decision support is largely because I'm a part of the SESI project. Oh, let's just say, this is joint work with Heidi Yang. He's over there. Yeah, okay. So he's just flown back from China, and he was doing the calculations on the plane. So we're going to show things. So we'll see what we come up with. Okay. Now, so we are both and Wei Sun, who is the person who owns the model. Well, who is our involvement with the model that we'll be talking about. Okay, so we're part of the SESI project, the National Centre for Energy Systems Integration. Okay, so it's EPSRC funded, involving a bunch of universities. So the concern is we have energy systems that are usually thought of in a very siloed way. What happens when you integrate them? What are the issues? And our role is basically UQ. Okay, so here are the kind of things. So we look at things at different kind of levels. from the level of sort of very great detail. Here's a particular very large building. How do we retrofit it to efficiently, given they're going to spend millions on this retrofit for a big building? It's an interesting and big problem with its own big model. The other scale, how does climate, likely changes in climate affect like the energy market? So you have climate models, you have energy market models. Okay? And then there's UQ basically for policy. So the example I'll give, and I'll put up a couple of more like finished examples at the end. So here's what an active electricity network looks like. There's some wind turbines, there's heat pumps, there's sort of things going in, and then there's places pulling energy out. And the particular example, so we're not going to do the whole network. For this example, we'll do a sub-network, well, a sub-aspect of the network. Okay, so here's a region. So I'm told the region is about the size of Durham, but we're not allowed to say exactly where it is. Okay, but the point is that they have detailed data over a year, for effectively at every household level, and for the amount of energy that was used, and what the weather was like, and etc. Okay, and so this is a question about investing in wind farms. So we have the options of building. Well, so at the planning level, we are considering the fact that there are 5 wind farms that we could build, and our choices would be build them or not, and if we do build them, how big do we make them? Okay. So we're planning to build 5, and okay. So now 3 wind farms are close to each other, so the wind data for that 3 is going to be common. The other 2 are in a different place. The reason we can't like put them together is because even though they may be in the same place, the ways that in this problem, these are connected into all of the houses. So there is a complete, so the representation inside that box, there's a lot going on in that box. Basically, there's the whole area. There's the way that each wind farm is meant to be linked into everything. Yep. So there's a lot, almost everything is hidden in that picture. It's going to be a computer model. Okay. So we have hourly demand data and hourly wind speed data. Okay, and now the demand, we're not worried about not making demand. Okay, you see that there is a grid supply point, so if we haven't got enough from the wind farms, the grid will supply. On the other hand, if we have too much, then in this particular problem we haven't got storage. Okay, so our problem is producing too much, not producing too little. Okay, so what we want to do is we want to produce like lots and lots of power, so that's good, but we don't want to produce too much because that would be wasteful. That's what stops us building like huge wind farms. Okay, so there we go. So the optimization problem, the pizza problem, is we want big power generation but small waste. Okay, so that's going to be our Pareto boundary. Okay, so we have the capacity of each wind farm, the demands and the wind levels. They're fixed over a year. We say, okay, I'm going to use this capacity, this capacity, this capacity, this capacity, this capacity, put it in the model and go. And what happens is that there is a complex optimization problem. So at each time point, the wind produces power that goes into the system. There is an optimal allocation to make the most use of it, and then we see how much we used and how much we wasted. And that optimization is what makes it the model actually take quite a long time. Well, I say quite a long time. A single evaluation will take about 10 seconds. You can imagine that as we make this problem bigger, as the wind farms do more and they interact with more things we have to choose, these eventually will become very complex functions. If you'd like to read about this, the general principles are in the one at the top. The exact version that we're actually talking about is the one in the middle, and there's a bit more detail about it in an IEEE paper down there. Okay, so if you're interested in the kind of things that people use for energy planning. So our objective is to maximize distributed power generation, conditional on overall waste. Okay, so we want DPG to be big and waste ratio, which comes out of the computer model, to be small. Now, the person who brought it to us, so Hailiang, was in Edinburgh talking to people about other general SESI things, and he talked to Wei Sun and said, here's his traditional optimization solution, okay, and like that. And so we thought it would be interesting to think about. Firstly, I mean, you can actually do a traditional optimization here because the model's fast enough. What is the general methodology, and then we'll see how it works. Secondly, there's just one solution there, and as I said for the pizzas, there's a lot of uncertainty here. There could be a lot of competing solutions that are about as good, some of which might more survive model discrepancy. So we want to think about sets of solutions. Okay? So let's think about challenges in traditional optimization. Firstly, if the function's expensive, then things can be expensive. Secondly, there's all the problems of local minima, etc. And then the second set of problems is that we really want a family of solutions. There will always be features of the solution which are important to the problem but didn't get in the model because they were hard to do. So there could be like subtleties about what we would like and what we wouldn't like, what's politically feasible, what's not. So really we want a class of solutions. And okay. And finally, that kind of direct optimization ignores like model discrepancy and things like that. Okay? So that's our aim. So what I want to talk about is I want to give you the tools. So if you think, okay, I quite like, I occasionally have to optimize under constraints, and I'm not quite sure. There are packages that would do this, something that you could control yourself. Okay, so here's a traditional optimization problem. I just want to make this thing as big as possible. Now I'm going to have to talk you through a little bit what we mean by history matching. It's a shame in the sense this isn't at the end of the week, because I think you're going to see some talks where people history match, and then I'll say what that history matching was. We're going to do it for optimization, but basically, and we'll talk more about the sense in which this is history matching. Okay, so history matching is about finding all of the, the way I usually do it is to find all of the input values such that when you run the function at those values, the outputs look quite a lot like history. Okay, so basically you're trying to find the inputs which make the function get close to something. So when we do an optimization, you can see that we have a criterion that we're trying to get under. In history matching, it would be distance to the thing, and the only but big difference between history matching traditionally and optimization is that I have to figure out what that t threshold is, because I need to work out where I want to get close to. Okay? So in order to do this, I'm going to need to emulate my expensive function. Now Derek said an interesting thing yesterday. He said we're all using the word emulator. Most people know, yeah, I know all about that. There may be some people who they keep hearing the word, but what exactly is it? So I thought, let's have a slide on emulation, which will allow me to make one point. Okay, so a function is expensive, we emulate it. What does that mean? That means that we build, okay, so we observe it at certain points, we build an uncertainty model for everywhere else. Okay, so that's what we mean by an emulator. So an emulator does two things. Firstly, it approximates the function, like the mean of the emulator will be like a kind of a surrogate model, and then it has all of the errors that we make. We have a stochastic assessment of the likely errors in these things, and it's correlated across the whole space. Okay? So we can quickly do things with the emulator that we couldn't do with the original, and we have a full probabilistic description of the errors we're making. So what does an emulator look like? Many different things. Most of the people here are creating slightly different ones. A common one is it's like a polynomial, for example, fit, or just plus a residual. Okay, so we have so that's our surface. Okay, which is, we call it the global part, because anywhere you sort of look, it has information about the quantity, and the residual because f is continuous. So the b's are continuous, so the difference between f and the global part is continuous. It's a continuous function. It tends any particular shape features we would have stuck in the global. So we do it. We have usually a stationary process, and we have to decide how smooth it is. So we have a correlation kernel, and there are many different kinds. The simplest one is this one. Okay, there we are, and we fit them using. You can imagine that there is a whole subject. Everybody has their own code, and there are many packages for fitting emulators, and we do diagnostics. Now, there are many differences to all of these things. The biggest difference, I think, is in people's philosophy. Some people basically take very, very, very simple mean functions, if anything, and let the Gaussian process do all the work. Other people, me very strongly, put a lot of work into constructing the mean function and hope that the Gaussian process or residual will soak up just little bits of variation at the end. And for many reasons, I prefer the latter, but people have different views. In fact, I said Gaussian process there, but you notice on there, I don't actually require a Gaussian process, because that would imply normality. All I put down is second order stationary. So the same mean for each x, the same, in fact 0, same variance for each x, and that correlation function. And I do that with one slide on how we do things. What is Bayes linear analysis? Everybody in this workshop and in the other workshops and everywhere says we have to do a probabilistic analysis, which is great, but it's heavy in terms of assumptions and it's heavy in terms of computations. Bayes linear analysis turns the whole thing around and it makes expectation the primitive, and it says rather than thinking about everything, I'm going to think about which expectations, variances and covariances I can specify and are relevant to the problem. Okay, so we gain in making a simpler uncertainty specification, a simpler and faster analysis, and in fact there are foundations for doing this. I mean, if you ask me, but isn't that like wrong? You know, and I say no, actually it's right, but that's a whole foundational talk that if anyone is interested, I'm happy to talk about. Okay? So just as Bayes' theorem is a single equation that takes you through Bayesian inference, there are two equations updating my mean, updating my variance for Bayes linear analysis. You will have seen them obviously many times in different ways. They take means and variances and turn them into adjusted versions. There are many things hidden in there. For example, Bayes' theorem is a special case of this, and you might think, oh, that's interesting. I didn't spot that, but you can look at that. Yeah. And then here's a book that can tell you all that you could possibly want to know. And with blood, there's a very short version in the stats reference online, this amazing thing, which is 7 pages that gets you to the heart of what we're doing. Anyway, so that's what we're using. So we're not going to talk a lot about computations because they're quick and easy. Again, so now let me get you to history matching. So here are a single input, a single output. We have 5 observations of this function. Here I've built my emulator for it behind using what I just told you. So the blue line is the expectation of the emulator. The red line is some uncertainty around the points. No uncertainty around the points was evaluated. Oh, I forgot to say, thanks to Ian Vernon, these are like his pictures, but they're very, I always find them very instructive. So there we have them, okay? And so there's no uncertainty at the points. Uncertainty grows if you move away. Now I'm now going to do a history match. So one input, one output, but I've got an observation. I want to know what x is. I want to do the inversion. So I have an observation. There it is, with error. Okay. So effectively, there's my inversion. Okay. So all the red points, they're just too far away. They're not going to cross. So the bounds on the emulator don't cross the bounds on the observation. So we remove them. The points to the left are not ruled out. Okay. Now that doesn't mean that that's necessarily the right answer, because there's still error in the emulator. So what we do, so that was the first wave, those 5 points. We now say, wait, okay, now we know we're in there, let's take another point or two in there, okay, and then re-emulate just inside. So when we get increased emulator accuracy in the important part, then that will reduce our emulator uncertainty in there, okay, and now the emulator is more accurate, and we can get down to effectively how closely we can actually match. Okay? So history matching is effectively doing that match, which is intuitive, and I've always found it sort of relatively easy to do, relatively, and scientists tend to find that interesting to know what data could match. Okay? And secondly, the key part of it, which is why it works, is it's hard to act accurate. And people say, well, let's do an emulator. Emulating is hard. It's a big, complicated function. So the whole crux of history matching is to put most of your effort in emulating where it actually matters. I mean, so that's a really important principle. And in particular, imagine that I'm history matching to a lot of data. I don't have to history match everything at once. I do a bit. I bring something else in. Later on, it becomes easier to emulate. So there's a whole reason for this to work. Okay? And the key part is that we're not finding the match, we're throwing away the not matches. So when I come to optimization, okay, I'm now going to do it the same way. I'm not going to go for the optimum, I'm going to remove what's not the optimum. Okay? So I take a sample of x values, I'm trying to minimize the function. For each input, I get upper and lower bounds from my emulator, for example, plus or minus 3 standard deviations using Puckelsheim's rule. I search X space and I find the minimum value of u of x. Let's call this u. And any x with Lx greater than u is clearly not going to be the minimum, so I can remove it from the space. So my first wave now is removing, I'm not trying to find the maximum at all, just removing the not maxima, and I just keep doing that. I do it in waves until I start getting solutions which are not varying very much and the lower bound. And a general comment that if I have constraints, I need to make sure that I apply them in the right sequence for that. Okay? But anyway, so optimization therefore is both, can be done in a history matching-y sort of way. We're catching all of the regions, hopefully, that are good. And we end up with sets, so we get that class of many solutions. And sometimes, I've presented it in its most efficient way. Sometimes we're less efficient, we just use thresholds. So let's do it for the example. So we're going to run about 4 waves each with 50 observations, 50 runs of the thing per wave. So we emulate adjusted R squared when we do the 50 runs and we do a polynomial, a third order polynomial fit to our wastage is about 0.97. It's a good approximation. Okay? And here's a leave one out cross validation. It's a diagnostic. So you leave one out, refit, and predict. So the validation looks okay. Okay? In fact, these are plus or minus 2 standard deviation bounds, I think. Okay? And so what do we do next? So we get the mean of the standard deviation of our output. So there are many things we could do. In fact, what Hailiang, for example, we chose to do is he found the lower 2% quartile of the expectation from the emulator, okay, and the value it was achieved at. He then says, let's add 2 standard deviations to that. So any quantity whose lower bound is bigger than that, we can actually remove from the space. So we remove all x for which that is true from our emulator, and that gets rid of 93% of the space. We now resample and we get, again, polynomial fits of about 0.96, a second leave one out validation. We now decide to start moving to fixed thresholds, because now we actually want to be careful that we don't break our constraint, and so we do a second sort of sweep, getting rid of another 88% of the remaining space. We then get another set of polynomials where they're adjusted R squared. We keep on going. We now start imposing the constraints that we don't want. We can get no wastage by not having any capacity, so we start imposing a capacity constraint, and we reduce it again. We keep on reducing, and so what this just says is as we reduce, we've done 4 waves where we actually evaluated the function. In wave 5, we now have, using our emulator, we create a further reduced space. This is now, all these points are pretty good for solutions. So we now have a solution set. Okay, so it's a very tiny fraction of the original space. We have an emulator for it, so we can interrogate it. We can say, I would like a solution where the capacities are all fairly similar, or I would like a solution where as few capacities we can build as few as possible. We can interrogate it and we can get different solutions. So here are just examples of the original solution and some of the things that we find just by evaluating the function in the solution space. So this is a method for finding sort of solution spaces for decision support. Now, because I see time is running out, a huge important problem is I haven't said anything about model discrepancy. So here were 3 slides that would show the kind of things that we would do for that. So just to make a comment that model discrepancy is really important and it can be integrated into the procedure. And if were you doing it for real, it would be hugely important to do this. So I need to get to that Pareto boundary. So we have our 2 functions. So A of C would be the capacity, F of C would be the wastage. We want A to be large, F to be small, and effectively we want that boundary. So, okay, there we go. So the Pareto boundary there is defined. It's a curve such that every point on the curve corresponds to at least one choice, and you can't beat both axes by any choice. Okay, so we want to find the Pareto boundary. We want to invert it into solution sets. And now there are 2 ways to do that. And I want to get through both very, very quickly, because I'd like to ask you which one do you think is better. Because I don't know. So the natural way is simply to sample and emulate, and you've got upper and lowers for each for F and for A, and all you then do is that you just eliminate points for which the upper of one sort of beats the lower of the other, and you just do that, and you just keep on doing that until the boundary appears with a set. Okay? And Now, just as a general comment, okay, so what I've said before is you resample and you re-emulate. Because you're going right across this thing here, you might chunk it and get different emulators for different bits, because we're now starting to be in different regimes. So there are a few technical points, but and the idea will be clear. So here we do that. So here's an example of us doing that. So the red line is, in fact, because it was a fast model, exactly, that is the Pareto boundary for power generated against waste. Here's the blue lines are our plus or minus errors on our guesses for that. We took 4 waves of 50 each time to get to that point, and we chunked the emulator into four bits, and we now have our solution set. And obviously, we could have probably been more efficient, but we're kind of getting it. And the fact that there's a variation is both bad. We haven't got it exactly, and good because it gives us more choices. There's probably a final stage of inference where we smooth this out. But anyway, let me say second method, so I'm going to hit it on time. So there's a different way of doing this. What I try to do is to find the whole Pareto boundary. I could instead aim to find individual points on the Pareto boundary. And so I would, for example, I could fix the total power consumption at one value, find the sort of the minimum wastage, and just keep on moving along, maybe to say like 5 points on the boundary. Okay, so we pick a fixed number of points. For each, we emulate and we minimize. Okay, and so I now have, I don't have the whole thing. I have this point, that point, that point, that point, and that point with error. And I've exactly got the one-dimensional sort of picture that I showed you at the beginning. So I now emulate the Pareto boundary. I have emulators for this, and this. So I emulate the emulators at every point. Okay. So what I do is I now have, by doing this method, this different slicing, I have a full emulation system for the whole curve. Okay. So I'm much more accurate at the points. I haven't investigated between them at all, but I have a full emulation that I can use. Okay. So there we go. So that's what I'm saying here. So I emulate. So rather than slicing it like that, like ham sandwich systems, rather than slicing it like that, I slice it like this, and then I fill in. Okay, so I'm almost done here. So we're just starting to do this. Here's the starting to do this. We start with one wave, sort of having our uncertainty at 5 points. You can see gradually as we tighten that, we'll basically pick the curve up. Okay? So concluding comments. Firstly, the history matching approach is kind of old school. People who have been around doing these things in stats for a long time, remodeling their response surfaces. It comes up in many contexts. Okay? And so it's a reminder that it's very useful in decision support to do this, and it's particularly good for finding classes of solutions which form the Pareto boundary. Secondly, Bayes linear methods are a great tool for doing this. There are two things I haven't talked about: model discrepancy, which wraps in naturally, and multi-level emulation. If that model is expensive to evaluate, we have many tricks to combine sort of levels to do this. And finally, my question again, I'm trying to find that Pareto boundary. Is it better to emulate and gradually shift up the whole space and move towards the boundary, or to identify individual points and then use smoothness ideas to create an emulation across? Now, if there's anybody who has an intuition on this, I mean, I would like to do it this way, where I take the individual points and then fill out, just because that seems kind of nice and interesting to try. But I have no idea whether that's just a fool's errand. So if anyone has an intuition as to which is the best way to get to this, I would be hugely interested to know. And finally, just a couple of references. So we've been talking about power systems. If you want to know, so here is some slightly more organized work we've done on power systems. So here's a couple of papers, one on transmission planning, again for the country, and one for modeling the long-term electricity supply. So you can kind of see the kind of models that we will apply these ideas to. Thank you very much.
Thanks, Michael. The questions?
If I understood correctly, you do not directly calculate the optimal solution, but rather focus on removing irrelevant ranges.
Yes.
And I would be interested in whether there are results on how close you actually get to the real optimal solution by doing so.
Yeah, okay, so very interesting question. Yeah, so we very much don't identify the optimum, but we identify a family of good solutions. Okay? Now, you can go through obviously more ways. So the question about when you stop, yeah, so when I showed originally the idea about being sort of tightly doing it, we could carry on and we could keep thinning out until we actually get to that point. Well, interesting question whether we could or whether we know by noise. What I tend to feel is that in our final set, you kind of see how different the solutions are. Yeah. So we have, effectively we decide on a kind of a tolerance. How different can we accept? Yeah. And of course, once it gets to the Pareto boundary, that becomes an even more interesting question because it's tolerance at every point. But there is information in what we do that can guide us about how well we've done.
Thank you.
Yeah, I wanted to say my preference was for 2 because smooth and monotonic are things that they're judgments we could definitely hold about Pareto front.
Yes, definitely.
And they're judgments we can build into our statistical models via kernels or what have you quite naturally. So and the other version doesn't have those in.
No.
So
no. I agree. So you think that I'd like that to be the right, but on the other hand, there is an error. I mean, in a sense, having actual observation sort of points all around, in some sense, fills out the space more. But in this way, you're actually whether you want to really identify these and smooth. I'm hoping that it's the second one because it's just more fun to do. But
there's a third method, which is classical in multi-objective optimization, which is aspiration point. You put a point outside, put a set of points outside, and find the closest point on the boundary. It's like sticking a rectangle into the boundary, and that will work even if it's not convex. It should work.
There's no requirement of convexity.
Check out aspiration point.
Yeah, but we should talk about that more because there are different ways. I mean, what I've done, in fact, is I haven't really told you how I find the Pareto boundary. All I've done is I just said eventually it will emerge from the calculations. So I feel that as we get close, these kind of the nuts and bolts of the calculations that we do.
You change your metric. You can have different metrics. If you can put in a plane, hyperplane, or this.
No, there's a lot of sort of fine tuning to make this, and how important that is it depends, I think, on the complexity of what we're doing.
Are there any other questions before we break for lunch? By the way, I didn't hear anything after pineapple and blue cheese.
You should try.
Anyway, okay, well,
if you have a poster in today's session, could you please put it up, if you haven't already, over lunch? The room's just behind you.
All right. Let's thank Michael one more time. All the students.